Hello everyone. In this video, we are going to discuss about the different methods of presentations through which we represent the rainfall data. So let's start. So till now we have seen that the rainfall that is recorded by a device which is named as the rain gauge station. Now the data which is collected by these rain gauge stations that can be presented by any of the following methods that we are going to discuss. The first method in that is known as the point rainfall. Now what is this point rainfall? So as we know that there is every one station in a representative area, and that station is installed with a rain gauge which is recording the rainfall. Now that station is representing the rainfall data of that particular station, and depending upon the need, this data can be obtained on the daily basis or in the every 7 days or monthly basis. That may be obtained also based upon the seasons, or that may be calculated for the complete year, that means the annual values, or there may be any type of period for which the data can be collected. Now these data points that we are collecting through the point rainfall, they are represented with a plot of magnitude of the rainfall versus chronological time in form of the bar chart. So if let's say this is the y-axis and this is the x-axis. On the x-axis we are representing the time in hours, and on the y-axis we are representing the rainfall in centimeters. So for 0 to first hour, let's say the rainfall that has occurred, that is of P1 magnitude. So this bar chart that will be representing this P1 bar. Now in the next hour, let's say the rainfall has increased and the total magnitude that has fallen in the form of the rainfall, that is, let's say P2. Then let's say that's after that suddenly it dropped, so that will be P3. In that way these bar charts are drawn. So these plot, they are convenient for obtaining the magnitude of the rainfall, but these are not convenient, and that is what is important. Because of this drawback or the limitation of these methods, we have moved on to the newer methods. So this type of data that is not convenient, for deciding the trend of the rainfall, that in what direction the rainfall is moving, so that we can predict about the magnitude of the rainfall for the next hour. Now this drawback that is eliminated by one of the advanced method, which is known as the moving average method, which we will see in a due course. Then the next method, that is known as the moving average method. Now what is this method? So in this method, the average data of every 3 to 5 consecutive years. What is important, that it must be consecutive years. Now these years that we have written as 3 to 5 years, that can be changed as per the convenience and the data which is available. So for example, if we are collecting the data from 2017, then 18, 19, 20 and 21. So we have collected the data for these 5 years. So we will take the average of these years, and that will be representing the rainfall data for these set of years. Then if we are taking, let's say, the previous one, so the next 5 will be like this. Similar, the sets of 5 years will be taken, or 3 to 5 years, that will be taken. So for example, in this we are taking the 3 years data as an average value. So for first, second and third, this will be the average value. Then for the second, third and fourth bar, this will be the average value. Then for third, fourth and fifth, this will be the average value. Similarly, we are getting the average value for the 3-year average. Now when we connect these points with the help of a curve that is plane and smooth, then we are getting the 3-year moving average curve. Now what it is helping us out? So what advantage is it providing? So this method is generally used for getting the frequency of the fluctuations, that how many fluctuations are there from the average value of the time series, and it enables us to show the trend or pattern of the rainfall. That means if the curve is moving in the upward direction, so we can predict that the next average will be somewhere like this. So that is what is the advantage of this moving average method over the other methods. So for the 3 years data, we will be taking the average. For example, the first average, that will be P1 plus P2 plus P3 divided by 3. Similarly, the next average will be P2 plus P3 plus P4 divided by 3. And in this way, we will be moving ahead. Moving on to the next method, that is known as the hydrograph. Now, what is this hydrograph? So, it is a plot of the intensity of the rainfall against the time interval. Now, what is this intensity of the rainfall? So this is the magnitude of the rainfall that has fallen at a particular place, and it has to be divided by the duration within which this rainfall has taken place. So because of that, this intensity, if we are having the certain units for the magnitude of the rainfall, and the duration is usually calculated as hours. So the unit of the intensity of the rainfall, that will be units per hour, or usually that is written as in centimeters per hour. So on the y-axis we will be representing the rainfall intensity, that will be in centimeters per hour, and on the x-axis we will be representing the time, which may be in minutes or in hours. Now this hydrograph, that is obtained from the mass curve of the rainfall only, because the slope of the mass curve at any point, that represents the intensity. Now what is this mass curve, that we will see in a while. Now this represent the data in the form of a bar chart. So let's say for the first 10 minutes, the intensity of the rainfall, that was low. That means initially the intensity was 10 centimeters per hour. In the next duration, in the next 10 minutes, the intensity has increased, and that is 15 centimeter per hour. Let's say after that it has suddenly increased and it is 25 centimeters per hour. So that is representing the intensity of the rainfall in a particular duration. Now what is the importance of this? This method is very convenient way of representing the characteristic of any storm, because we are looking at this data, so we can say that the storm is surging, and after that this storm will be passing out. So that plays an important role in the development of the design storm, because every hydraulic structure that is designed for a certain storm value. So if we are already aware, depending upon the location and depending upon the rainfall data for that particular location, then we would be able to design the particular hydraulic structure for a storm value. And the area under the hydrograph, that represents the total precipitation received in that period. That means this area under the hydrograph, that represents the total precipitation that is received in that period. For example, for the first 10 minutes, the intensity was 10 centimeter per hour. So for So for first 10 minutes in 1 hour, the rainfall that has occurred, that is 10 centimeter. That is the meaning of the intensity. Now this 1 hour can be written as 60 minutes. So that means in 60 minutes we are having 10 centimeter of the rainfall. So for the 10 minutes duration, the intensity of the rainfall, that will be 10 centimeter divided by 60 into 10. So this is 10 by 6 centimeter of the rainfall in that particular 10 minutes. So that's why the area under the hydrograph, that is representing the total precipitation which is received in that duration. So we have calculated for this duration only. So this is the magnitude or the total precipitation which is received in the first 10 minutes. Moving on to the next method. Now this is known as the mass curve of the rainfall. Now what is that? So if the total accumulated precipitation is plotted against the time in the chronological order. For example, let's say we are having the data from 2012, 13, 14. In this way we are moving ahead, and then 2019, 2020, then 21, then 22. So this is the data for the past 10 years. Now in the 2012, let's say the precipitation that has occurred in that particular year, that is 100 centimeter. Then for the next year it is 90 centimeter, then 95. In that way we are moving ahead, and the data for the latest year, that is 102 centimeters, and let's say this is 106 centimeters. So for the first year, the rainfall that has occurred, that is 100 centimeter. For the next 2 years the data will be 190 centimeter. That is the accumulated value. But in this method we are not taking the data for each year, we are taking the data for each day, and those days data that is collected and accumulated and then represented in the form of a curve which is known as the mass curve of the rainfall. So this mass, that is representing the accumulation of the data for a certain period. So if the total accumulated precipitation that is plotted against the time, the curve obtained, that is known as the mass curve of the storm. So this curve that rises steeply in the beginning and then tends to become constant. Why is that? So let's say for the first day, the data that was collected, let's say for the first day, the accumulated precipitation, that is 2 centimeter. In the next day, let's say another 2 centimeter of the rainfall has occurred. So for the 2 days data, the point will be moving on to the fourth. Then for the next 2 days, the rainfall that has occurred, that is let's say 6 centimeter. So the accumulated rainfall will be 10 centimeter. In this way, the data or the curve is moving ahead and is rising steeply. After that, there will be a certain plateau. If there is a gap in the storm, in that particular plateau region, there will be no increase in the accumulated precipitation. So whatever rainfall was obtained for the fifth day, that will be the same on the sixth day. So that means between this duration there was no rainfall, and therefore the first storm is classified before this and the next storm will be classified after this. And the slope at any point of the mass curve, let's say if we are calculating the slope here, so the slope is always calculated from the horizontal. So this theta 1 value, if we are calculating this slope in terms of theta, this slope of mass curve at any point, that represents the intensity of rainfall at a particular duration. Now, when we studied the different type of rain gauges, so in that we have seen the weighing bucket type and the float type data of the rain gauge that is obtained in the form of the mass curve, because in those methods the data was getting accumulated for the entire day. So at the end of the day we were getting something like this, which is known as the mass curve of the rainfall. Moving on to the next one, which is known as the depth area duration relationship, that is the DAD relationship. Now the aerial characteristic storm of a given duration that is reflected by this depth area duration relationship. Such a relationship is shown in the figure which is attached here. Now different such curves will be obtained for the different storms of a given duration as shown in the figure. Now from here a maximum observed value is determined. Now what it is representing graphically, the relation between the progressively decreasing average depth of the rainfall. So as you can see on the y-axis we have represented the average depth in centimeters. On the x-axis we have represented the area in square kilometer. So the each depth area duration curve that is representing a particular duration. So if we select a particular duration, for example for 18 hours, so we can see that as the area is increasing, the depth goes on decreasing. So the relation that has been represented by this depth area duration curve, that is between the progressively decreasing average depth of the rainfall over a progressively increasing area. So the area is increasing in this direction, so the depth is decreasing, and that is for a given duration. That is what is important. So obviously when the area is increasing, so in this method what we are having, we have to assume certain assumptions for the analysis part. So the analysis of a particular storm that is done by this relationship just to determine the largest average depth of the rainfall which falls on the various sizes of the area during a particular duration. There are certain assumptions which are made in the analysis of this method. The assumption is that the intensity of the storm that is constant. That means if initially at the end of the 1 hour the intensity was 20 centimeters per hour, that is very high. So if in the 1 hour the rainfall that is falling or being recorded by the rain gauges, if that is 20 centimeter, that will remain at the end of the 5th hour, or at the end of the 10th hour, or at the end of the storm. Whatever be the duration, the intensity will remain same. The second assumption, and that is the most important one, that the center of the storm, there will be certain I in the storm at which the center of the storm will be located, that coincides with the location of the rain gauge. So the center of the storm that coincides with the location of the rain gauge. These two are the basic assumptions. So if this is the rain gauge at which the data collected is P naught. This is representing a certain area, let's say that is A naught. Then we will select a larger area, let's say that is A1, for which the average rainfall is P1 bar. Then we will increase the area again and we will select the higher area, let's say that is representing an average rainfall of P2 bar for A2 area. Now when we are selecting the area, we have to keep certain points in mind, that the total A2 area, the A2 area that is not equal to the A1 plus A naught. So it should not happen that initially the area was 100 square kilometer, then the next area is 200, and the last area is 300. Otherwise, this will be the combination of the first two areas. Now, the curve which is representing the depth area duration, that is represented by this way. Now, what is important in this case is that this curve is being plotted on a semi-log scale. That is the common confusion when you directly refer the textbooks, because in that there is nothing which is mentioned as such. So this curve is on the semi-log scale. As you can see, the data is for the 10th value, then for 100th, then for 1000th, then for 5000. So in this way, the data is increasing. So the area is represented on the log scale. And for such scale, the curve shape is of the convex outwards. But if we draw both the data simultaneously on a normal scale, that is the depth on the y-axis, which is the average depth against the area, then the curve that we obtain, that is of the concavity, and this will be the concave upwards. Now for a particular duration, the average depth that goes on decreasing as we change the area, or rather we increase the area. Now this relation for the particular duration that has been obtained by certain scientists, and that is represented in the form of P is equal to P naught into e raised to the power minus k upon a to the power n. That is representing the variation of the rainfall in a particular area, where P is the average depth in centimeter over an area of a square kilometer. P naught is the highest amount of rainfall in centimeter at the center of the storm, and this k and n value, these are the constants for a given region. Now on the basis of the number of studies in the North India, two scientists, that is Dhar and Bhattacharya, they have computed the values of these constants, that is for k and n, for the different durations. So if the duration in day, if that is represented by, if that is calculated for one day, the k constant, that is 8.5 into 10 raised to the power minus 4, n value is 0.66. For 2 days, this value is 9.8 into 10 raised to the power minus 4, and n value is 0.63. And this third, for the 3 days, this value is 1.7 into 10 raised to the power minus 3, and n value is 0.5961. The actual curve for the depth area duration, that is for different duration, that is represented in this form. Now as the duration is increasing, that is for 2 hours, then for 4 hours, then for 6 hours, so as we are increasing the duration, the curve is moving outwards, and this is representing the first quadrant limb. This is resembling the first quadrant limb of a hyperbola. That is the mathematical significance of this curve. Moving on to the last method of representing the data, that is known as the intensity duration frequency curve, that is known as the IDF curves. Now the rainfall at a place, that can be defined completely if the intensities, durations and the frequency at various storms at that particular place, they are known to us. So when an intense rain occurs, if the intensity of the rainfall, if that is very high, its magnitude and the duration that is known from the meteorological readings. So for the magnitudes and the duration, we are already having the data. Now this data can be used to determine the frequencies of the different rains. Now that frequency data for the storm of various duration, that is represented in the form of the intensity duration frequency curve. So what is this? So it is a plot of the average rainfall intensity in centimeters per hour and the duration in the minutes. So for a given frequency, for a particular frequency, the plot is between the average rainfall intensity and the duration. So it is a graphical representation which is given by the equation as Imax, which is representing the maximum intensity of the rainfall, that is equal to kt raised to the power x upon d plus a to the power n, where this Imax, that is representing the maximum intensity of the rainfall in that place, then this capital T, that is known as the return period. That means after what duration this particular rainfall or this rainfall of a particular intensity that will return to the catchment area which is under the consideration. This capital D, that is representing the duration of the rainfall, while these K, X, N and A, these are the constants which are having different value depending upon the locations of these stations. The curve that we get for the intensity duration frequency plots, that is represented by these concave curves. Now as the return period is increasing, for example for 10 days or for 10 years, for 20 years, let's say this is for 100 years. So this will be the plot between the intensity and the duration, and this is the frequency which is increasing, which is increasing, or rather this is the return period which is increasing in the outward direction. So the frequency is decreasing. That means this particular storm that has been highlighted, that is repeating after every 100 years. So the frequency is of 100 years. So that is very less chances of the certain type of storm. So if we select a particular curve, let's say we are selecting a curve that is representing the storm which occurs after every 10 years. So for a particular return period, as the duration is increasing, the intensity of the rainfall, that is decreasing, because you can see that whenever a storm occurs in a certain place, the magnitude of the rainfall, that is very high, but that occurs for a very small time. Incessant, that means if the rainfall is for a longer period, then the intensity of the rainfall with which it is falling, that will be comparatively lesser. I would not say that it is very low, but it is comparatively lesser, and that is what is represented by these intensity duration frequency curves. Now that completes the representation of the rainfall data. Now in the next video we will take a look at the abstraction from the precipitation, that what type of abstractions are there, and after those abstractions the component of the rainfall that we are having, that is known as the runoff, that we are going to discuss. So thank you.